We've finished up functions now. We've looked at injective, surjective, bijective, when inverses exist. And one of the reasons we want to build all of those tools is because we want those to study cardinality. We want to study the sizes of sets. It's the last topic we're going to do in this course. We can prove some really interesting results about infinity. But before we do that, we need one last proof technique, and that's proof by contradiction. And one of the reasons we leave this quite late in the course is because when people are introduced to it, well, A, it can be a little bit confusing, but B, people can end up trying to use it everywhere. And so we want to make sure we have plenty of practice with direct, contrapositive, proof by cases, those style of proof and induction, so that we're very, very familiar with them and familiar with how the logic works, so that when we get to proof by contradiction, we already have those other methods really secure in our thinking. So let's look at proof by contradiction. As I said, I'm going to start with a little bit of warning. And warning one is when you have a fancy new hammer or any nice new fancy tool, if you have a fancy new hammer, it's tempting to see nails everywhere. That is, you try to use it everywhere, even where it's maybe not appropriate. So along those lines, warning, please, just once you've learnt proof by contradiction, you don't have to use it for everything. You can use other techniques. So please don't use proof by contradiction for everything. But there are definitely some places where it works really well, which we'll see. Now, also a slight warning here is that proof by contradiction, when you first see it, can be quite confusing because, well, you kind of assume something that's false, that is, you assume garbage, and you do some work and so forth, and so get to something that is always false as a conclusion, and so you get to something that's from garbage, we get to something that's definitely garbage, and from garbage to garbage, we somehow conclude truth. And that can be very confusing, except we'll have two rather important bits of logic along the way here that will really help us make sense of why what can appear at the surface to be a very strange method actually makes you understand why it works and why it can be quite powerful. So let's look at these two bits of logic. So proof by contradiction relies on two things. It relies on the law of the excluded middle and on a type of deduction called modus tollens. So the law of the excluded middle we've seen before in this course, and is basically just the statement that, well, if we have a statement, then either it is true or its negation is true. So that is, P or not P is a tautology. Okay, so a statement is true or its negation is true. Now, the other bit of logic we're going to need is modus tollens, this type of deduction, which is something with kind of like contrapositive. Namely, if we know the implication P implies Q is true, and we also know that the hypothesis is false, then we must conclude that the conclusion is false. Okay, so this is modus ponens. Remember we saw before that if P implies Q is true and P is true, then we know Q is true. So this is sort of modus ponens but applied to the contrapositive. If we know P implies Q is true and Q is false, then P must also be false. Okay, and you can convince yourself of that by looking at the truth table. So now, armed with these two bits of logic, we can understand what happens with a proof by contradiction. So let's just look at the structure of a proof by contradiction before we actually look at a specific example. So let's say we want to prove, hey, the statement P is true. That is what we've been doing all the way through this course. So using a proof by contradiction, our proof will go something along the following lines. We'll tell the reader, hey, we're going to prove this result by contradiction, so I'm not going to actually assume this is true, I'm going to actually assume that it's false. That is, I'm going to assume its negation is true. Okay, this is one of the reasons we have to make sure we understand and negate statements earlier on in the course. Now, after we've assumed that the negation of this statement is true, which really seems like a strange thing to do it, we prove a chain of implications. Okay, so we prove that, hey, the negation of P tells me some other statement P1, P1 tells me P2, P3 implies P4 and so forth, just like we would with a normal direct proof. But now we're starting from the assumption that the statement we want is actually false. So we go through this chain of implications, not P implies P1, implies P2, implies P3 and so forth, all the way to Pn, and then Pn implies a contradiction, a statement that's always false. So something like 0 equals 1. Okay, so a contradiction, something that's always false. Now, this is where we can apply modus tollens. Modus tollens tells us, hey, if this is false, then Pn must be false, because I know that implication is true. So if Pn is false, then I know Pn minus 1 is false, Pn minus 2, Pn minus 3, all the way back up this chain of implications to tell me that P1 is false, and so not P is false. And so This is where we need the law of the excluded middle. So law of excluded middle then tells me, hey, if this is false, P must be true. So this is slightly weird when you first see it, but it's an extremely useful, powerful technique. So let's just go through that again. We're going to assume that negation is actually true. We build this chain of implications starting from that negation and reaching a contradiction, hence proof by contradiction. Because this is always false, we can go backwards up this chain of implications by modus tollens to realize that this is false, and so the original statement must be true via the law of excluded middle. So let's see this in action. So here's a very simple example. There's no smallest positive real number. So to a proof by contradiction, the first thing we're going to assume is assume to the contrary, and this thing here is just a little warning that's telling the reader, hey, proof by contradiction is about to happen. So assume to the contrary that there does exist a smallest positive real number. Okay, so just the negation of this statement. And let's denote it by the symbol Q. Well, from Q, notice that we can make a new number R, which is Q divided by 2. And that's also positive and strictly smaller than Q. So R is positive real number that is smaller than Q. And this gives us a contradiction because our assumption was that Q was the smallest possible real number, and we've just found something smaller. So Q is both the smallest real number and also not the smallest. So that's a contradiction. So that contradiction that tells us, hey, our initial assumption that there is a smallest real number must be false, and so there is no smallest real number. Now let's just analyze this proof a little bit further. What just happened? Well, start with, law of the excluded middle tells us that, hey, either P is true or not P is true. We just proved a chain of implications that, hey, if not P is true, then we can find a smallest real number. We know that this implication is true. From that implication, we then proved another implication. If we know Q, then we can construct a smaller positive real number, R, which is Q divided by 2. Now, if we have that smaller real number, then we know that Q is both the smallest and not the smallest. And that's a contradiction because that's of the form, hey, P, well, let's not call it P, let's call it Q and not Q. This is a statement which is always false. Q is smallest and it's not smallest. Okay, smallestest, oh, that's a bit of a typo there. I'll fix that when we upload. So this is a contradiction. And then we're applying modus tollens to tell us, hey, this is false, so that must be false. That's false, so that must be false. That's false, so that must be false. All the way back up that chain of implications to tell us, hey, not P isn't actually true. So by the law of the excluded middle, our original statement is true. Okay. Let's stop there.